Hello, everyone. So this is Isabel with Wisconsin Land and Water, and thank you for joining us today. I'm just going to give my little introductory spiel while people trickle in. So as you just heard, I am going to be recording this webinar, and it'll be posted on the Wisconsin Land and Water website at some point in the near future. And I'll also send you the link when it is available, as well as a link to the evaluation. The link for the recording is going to be the same as the one I sent out with all of the resources that we're using, and I'll put that in the chat right after this so that you'll have it accessible as Andrew goes along. So today our presentation will be using STEPL or STEPL, I'm not sure how we're pronouncing that acronym, or PLET or PLET, with streambank or gully erosion control projects. And our presenter today is Andrew Craig with Wisconsin DNR. As we go through it, feel free to put questions throughout the presentation in the chat line, which is at the bottom toolbar, and we'll have a few spaces that we can answer them throughout. So feel free to submit a question at any point and we'll get them answered. And so I think that's about it for me. Without any further ado, Andrew, you are good to take it away.
Okay, thanks, Isabel. Can you hear me okay? All right,
yes.
Great.
Yep.
So we're underway here. Thanks everybody for joining us today. Some of you are familiar with who I am. I'm Andrew Craig. I work for Wisconsin DNR as the watershed planning coordinator, statewide effort. I saw in some of the participants, I've worked with some of you individually on watershed-based plans, and then there's some others I haven't. What we're going to be trying to cover today is a specific aspect of watershed-based plans, and it also can be some common questions that you may have in some of the, if you're a county employee and doing some soil water conservation practices like stabilizing gully erosion or doing some type of stream bank restoration projects, which is fairly common in our state. This webinar is designed to kind of answer those basic questions of how can you model or estimate the load reductions from either stabilizing a gully or stabilizing sections of stream bank that are receding or eroding. And if you are getting a grant, for example, or you're reporting out for your land water plan, you can say, yeah, we did these practices. You can show the pictures and you can then include some of the estimated load reductions. So that's what I'm going to try to cover today. The genesis for this, I'm Stacy Den from Department of Agriculture's attending today. She was the one that initially contacted me. Stacy works with a series of 14 counties in the northern part of our state. And she said, can you provide some type of overview or training like this, because some of the counties have been asking me or the group has been asking these type of common questions. And I said, sure. And then we decided, like, why not do the whole webinar for the statewide basis, because this doesn't just apply this training just to those parts of the state. So I see Isabel's put up the resources for STEPL and PLET. Those are the tools I'm going to be giving an overview of today. And so I'll get started on that right now. So let me share my screen. I don't have a formal PowerPoint or anything. I'm just going to try to walk you through to where the web pages are and then actually use the tool today step by step and show you those things. So let me get started here. So let's begin with the EPA web pages where STEPL and PLET are shown. STEPL, some people say steeple, Isabel, like you did, stands for spreadsheet tool to estimate pollutant loads. It's a basic tool developed by USEPA for states, local governments, and others to estimate load reductions from practices at a variety of scales, a project scale, a site scale, or a watershed scale. And the reason why we have STEPL and PLET, which is the pollutant load estimation tool, is EPA transitioned from STEPL to PLET recently in April 2022. And PLET pollution load estimation tool is a more efficient approach to modeling needs. STEPL is a spreadsheet-based tool, and there are, for some of you that have used STEPL on this call today, there's issues with your machine and what version of Excel you may have, and the formatting that you download STEPL from EPA's webpage may not be compatible, or it can be frustrating. It may not show all the functionality or slow down. So what EPA did is said there's got to be a better, more efficient way to use these tools. So they came up with PLET. PLET's basically the same thing as STEPL in terms of its outputs and inputs. It's just a web-based platform versus a spreadsheet-based platform. So that's the big difference. So this is the STEPL webpage where you can figure out what STEPL is, what it can do, the documentation of how to use it. Over here is the PLET page, and fairly recently, like in the last week and a half, they added this additional link called training material for PLET, which has I'll click here right now. There's a actual training video you can watch. It's just like what we're going to be doing today, except it goes through all the aspects of PLET, not just gullies and stream banks that we'll be covering today. So if you want to go back and watch this video, I'm letting you know it's right here. It's just a YouTube video. Give it a review if you want to know about the full capacity of what PLET is, how to navigate through the screens, and what it can do. Today I'll be using PLET because it's more efficient, like I explained earlier with you. So let me bring up that right now. So if you go to PLET, pollution load estimation tool at EPA, you have to create an account because it's a web-based platform. It's real easy. It's your email and a user ID. So I'm going to do that right now. And then put in my password. And log in. So here's Andrew's web-based platform, and you can see this is the page you'll initially see when you log into PLET. And so now I'll go through some of the basic navigations of how you get started here. You can see I did create a project already in preparation for this. I'll be kind of repeating some of the same steps here. But the main thing you can do, the training video is up here on the right. There's the user guide. You can get it right here. And then the first thing you want to do to use PLET after you watch this or read the guide which we'll go through these steps as well, is to create a new model. And so you just click on the link, the button up here. And okay, worked great. So then you get this screen. And here you can name your project, and I'll just type in, because we're going to go to the Marengo watershed today as an example. And I'm going to say it's a Marengo stream bank project. And I'll select our state. And then after you click these two items in here, additional information comes up. And this is where you have two options to select the watershed you want. That, let's say you've done a stream bank or gully conservation project where you've stabilized some gullies or stabilized some stream banks. You've done some of the inventory work on the ground of estimating where the stream banks are eroding and the type of erosion and things like that. This tool can help you quantify what the loading was before the project was completed and how much load reduction of pollutants occurred after the project was completed. To do that, you got to pick your watershed first of where the project is. So I'm going to do that right now. There's two options here. You can, if you know that these are HUC 12 watersheds, there's 12 digits, that's what the HUC 12. You can pick here from the list, or you can go and this is kind of a cool feature, you can just zoom right in to, if you know where the watershed is, and pick your HUC 12 by just clicking on the map. And this is the watershed I wanted to pick today for the training. So if you double click on it and hit submit, it will select this watershed you identify. And what's great about PLET is that once you select the watershed, it has a database that's connected to it, and it'll automatically populate a lot of the inputs for this watershed from 2012 land use cover and some of the other databases that EPA has as of 2012 that they use to populate PLET or STEPL. In the spreadsheet tool, you have to go, there's a separate file that you have to go look up your watershed and then import all this information, which you can do, but this is a lot faster. So that's why I'm covering PLET today. It's a lot simpler this way. So everybody can see the screen now that I'm on. I'll start at the top and work my way through the bottom. So here's the same project that we identified, and the Marengo River watershed. You want to make sure that here's the county, and there's a weather station here. There are several weather stations by county. You want to pick the weather station that's closest to where you're at, and this one was Ironwood. There are some other buttons down below here, and this gets into kind of if you want to share this project with somebody else. If you want to make a copy of it, you can, and name it like project 1, so you can start doing some scenarios of this or that, so you don't mess with your original one. You can always delete copies or draft modeling, and you can download information from input data server, which is some of the information I was referring to down here. Here on this row, you can also add watersheds to this project. If you want to say we're doing work in this HUC 12 and the adjacent one, you can add one. I won't do that right now, but that's another functionality. You can delete watersheds, and then there are these other tabs here, and the one we'll be working with here today is gullies and stream banks. And there's urban BMPs and manure and BMP calculator, which we will not be getting into today. The other training video that I mentioned does. There are 4 main tabs here that relate to PLET or STEPL, and these are the inputs tab, which is shown, the BMPs tab, where you add additional practices. There's the total loads tab, which PLET estimates based on the inputs what type of loading might be occurring of pollutants based on land use and these different sources in the watershed. I'll be coming back and showing this for you today, and we're just going to be concentrating on the gullies and the stream banks component. We're not going to really focus on cropland or pasture land or forest during this training. And then there's some additional reference tables if you want to get into animal units and those soil properties and things like that. So the question at hand is we do a gully or a stream bank restoration project, how much load reduction can be achieved? I'll now take you through the steps of how to do that in PLET. So like I said, gullies and stream banks is what you want to select here. And right now, what I'm going to pause here for a moment and show you another screen about that and talk a little bit about the field work you're doing to populate this model, because that's really important. Because if you don't do good field work, you're not going to put accurate inputs into this model, and you won't get accurate outputs. So I want to emphasize a few of those things here today. The steps that we're going to go through, we'll do both the gully steps and the stream bank steps. I'm going to start with stream bank and I'll come back and do gully second. Is the steps we're going to follow. And as I click on this, you'll see which additional cells will come up, and you have to put some inputs into what type of stream bank recession and rates are as part of the project. So before I do that, though, I do want to emphasize this appendix. This is from a DNR guidance document for water quality trading that focuses on stream bank stabilization. And the parts of this guidance that I think are very relevant to the discussion today are the photos and some of the methodology laid out in this guidance document. And my understanding is Isabel has included this as part of the training session today, or we'll make it available so you can come back and look at it. You can also find this on our webpage if you type in water quality trading and go to the guidance document. It's the 2020 guidance. So let me scroll down here. So this is the part of the document that I think is really relevant to the field work you may be doing as part of the project, which is delineate which areas are eroding, measuring how fast they're eroding, and then and so forth. So this gets into where erosion may occur, what they look like, and then these pictures, which is what I wanted to get to.
Andrew,
so, yes.
I don't believe that we are seeing the document you're talking about on the screen right now.
Okay, let me stop sharing and I will reshare, because that's what this happens sometimes.
Yes,
thanks.
Absolutely.
Let me pick the right one here. All right, thanks for getting the hook there, Isabel, and giving me back on track. Sorry about that, everybody. So this is can everybody see the guidance document now?
Yes.
Okay, great. So like I said, this is Appendix F, and there are pictures down here that talk about what are techniques for stabilizing stream banks, what criteria to look for. And these are the pictures I wanted to show you. So on the left here, in a stream bank project, you want to put accurate inputs into the model to calculate accurate load reductions. On the left here is one site where there's active erosion occurring across the entire project area, for example. So you would want to measure or estimate the recession rates for this entire length or this entire site. On the right here, you may survey a section of stream that may be, let's say, 1,000 feet long, but it won't be continuously eroding along that entire 1,000 feet. There may be just portions where erosion occurring, and the areas that are eroding are the portions of the stream bank that you want to put into PLET to model them. You do not want to assume that the entire site is eroding at this rate if it's not entirely eroding like it is on the left. Only portions are. A couple more photos real quick here. PLET requires you to put in the bank height and the bank length of the eroding areas. And so there could be an entire erosion length, like I said, showed in that picture up above. The height, however, is measured from basically the ordinary high water mark at a diagonal angle to near the top of the bank. It's not a vertical measurement, it's kind of an angular measurement that you're paralleling the bank, and that's the height that you want to measure. And if you have multiple areas of erosion within the section of stream bank you may have been inventorying, you're going to want to take multiple height measurements and write those down and input them into the model to accurately assess the total erosion and pollutant loading from the cumulative of, let's say there's 4 or 5 of these sections along the section of stream bank you inventory. Okay, so I'm gonna stop sharing this and go back to the and reshare the PLET now. Okay, everybody can see this? I hope so.
Yes, we can.
Okay, great. So we're back where we started. Again, inputs are really important. You want to have some accurate dimensions of the stream banks or the gullies for that matter. And now I'll go through the steps. So what we're going to do here first is the stream bank. And like I said, I'm going to click stream bank here. And once you click on this button, you want to say, yeah, we're going to do a stream bank, and this is the watershed where it's located. And like I explained a moment ago, in this example I'm going to give, let's say there's a couple sections that are eroding significantly, and a couple sections of the stream bank that are eroding at a lesser rate than that, of a minor lateral recession rate. So I'm going to name each one of those type of categories by just using the letter A. And let's say there's 1,000 feet of stream bank that you evaluated on the project, and 100 feet of it had a more severe amount of recession. And the height of that was, let's say the measurement that I showed you was about 6 feet on that angle. The next thing you pick after you assigned this type of category of stream bank erosion is the recession rate. And there's 4 categories here: slight, moderate, severe, very severe. If you want to know what these mean, click more information right here and the definitions pop up. These are carried over from NRCS stream bank erosion tools, and they have a similar tool to PLET that's where this came from, this information. And it's basically a way to define how fast a stream bank is receding. And there's a slight, moderate, severe, and very severe categories with some criteria or descriptions. So if you're going to do stream bank work and you want to estimate, put this into the model, you want to use this criteria when you're doing your inventory work and write this stuff down so you can input it later. In this example, I'm going to say there is 100 feet of severe erosion where there's a lot of bare bank and a lot of tree roots are exposed and stumps and slag. So this is a pretty big recession rate, 0.3 to a half foot per year. Once you put in the category, it populates these numbers that you see here. The next thing you have to put in here is the BMP efficiency. And what this means is, are there any BMPs applied to this stream bank right now? And the answer is no, so you put in 0. I'll come back and we're going to change this number a little bit later to account for the practices to stabilize the banks. Another input you have to put into, and this requires a little knowledge of soils and inventory of your site. What type of textural soil class is found within this watershed or the area you're evaluating? In the Marengo River watershed, it's a clay plain where that's the Huck 12 that I selected. So I'm going to pick clay soils for that. It may be different for other sites that where you're located. Once you pick clay textural class, and this is like, you want to pick the one that best matches up to the area that is severely eroding and match that up. Once you pick clay, you can then, PLET will automatically assign these other factors. Right now, there is no load reduction because the BMP efficiency is set at 0. Okay, so those are kind of the steps of, I'm going to repeat this 2 more times for different recession rates and different lengths of erosion, because in this hypothetical example, there's 3 areas were inventoried of erosion, and they're at different categories. So the first section is right here. This kind of summarizes what we just inputted. There was a area of erosion. We labeled it area A. It was 100 feet long. This is the height, and so on and so forth. So now I'm going to do the same step again, more quickly this time. Pick the same watershed. I'm going to call this area B. And this was, I'm just going to say hypothetically 200 feet. And the height of this area was a little less. It was only 4 feet high. And the recession rate was slight. So not a lot of exposed roots. It's just, this is a minor recession rate. 0 on the efficiency again. And then I'm going to pick clay as well, because it's pretty much clay throughout this area that was inventoried. And I'll click submit. Now you've got area A with the severe recession and area B with the slight erosion rate. My hypothetical example here, it's 1,000 feet of area that was evaluated. You're only putting in the areas that are eroding. The areas that are not eroding, you do not have to include in the model. I'll pick one more here. I'll do this real quickly again. I'll name this area C. And I'll say this is 100 feet length. And we measured the height in this area and it was 5 feet. Recession rate was moderate. So I'm doing 3 categories in this example. And the clay, and hit submit. So here's these 3 categories. Of 1,000 feet, 400 feet was eroding at different categories. And in some stream bank projects, you want to try to, as accurately as you can, put in these different categories that reflect what's actually happening on the project. In some projects, you may have only moderate or slight or severe. It's all based on what inventory work you do for the stream bank project. Okay, so now what happens next? What do? You've put the inputs in here. On the right here, you can see down below, there is a load determined based upon these inputs for this watershed, this type of recession rate, this soil class type, and so forth. So how do you take this and put it in some format that says, here's our baseline, if you will, of erosion of stream banks? And the way to do that is to hit close here. Oh, hang on, it's going through this. So now we're back to where we started. We went to gullies and stream banks, put all these inputs in, and we went back here to the starting screen, and you can go to loads. And what was all zeros before, we now have these loading rates here identified for nitrogen, phosphorus, BOD, and sediment. The 2 factors that are more relevant to many stream bank projects is phosphorus reduction and sediment reduction. If this is a project in like a TMDL area or an area of a watershed where you're trying to reduce phosphorus or sediment loading, even if it's not in the TMDL, those are the values that you want to try to quantify and estimate. And you have done that here. So there's a couple options here. You can just do screenshots of this if you want, and then we'll go back and add practices, stabilization practices to reduce these to a smaller number, and then take a second screenshot. Or you can go up here where it says download. I'm going to click that right now. And what PLET will do is you can download this to an Excel spreadsheet, which I'm going to open up right now. And the same information that was shown on the web-based platform has now been transferred to Excel here. And there's 3 subtabs down here. Isabel, can everybody see this? I just want to make sure everyone's following along.
I believe so.
Okay, great. So once you download this in Excel, you want to click on this second tab, Land Uses.
Oh, I'm sorry. So you are intending to have an Excel sheet open right now?
I am, yes.
Okay, yes, we cannot see the Excel sheet.
Okay, let me
Sorry
stop
about
and
that.
reshare. That's fine. Hang on. Okay, now can you see the Excel sheet?
Yes, I can see it perfectly.
Okay, great. And can you see this in the background where it says download? Or just the Excel spreadsheet?
I can only see the Excel spreadsheet right now.
Okay, that's the active screen then. All right. Well, by clicking the download button that I showed earlier, this spreadsheet comes up. It comes loaded and it looks like this when you first get it. And there's these 3 tabs at the bottom that I was explaining a moment ago. The one you want to click is the second tab, total load by land uses. And this is the same information that was shown on the web-based platform screen a moment ago. It gives you the sources, nitrogen, phosphorus, BOD, and sediment loads. And these are the same numbers that we were looking at a moment ago. Oh, well, that was fun. Let me go back to sharing the screen again. Okay, can everybody see the Excel spreadsheet again?
Yes, we can.
All right, so I'm going to pull these columns out. And again, I think what happened was I unsaved the file or made it so I could edit it. So this is the same information that was on the web-based platform, and this is your current loading for streambank. What I recommend is you highlight this and just paste it down here. And we're going to do this again after adding some practices to get the reduced numbers. And then in Excel, you can quickly do, here's where we were currently, here's where we were after BMPs, and then you'll get your reduction. And from a reporting standpoint, I mean, you can report this in different ways. I like Excel because it's pretty easy, and then you can do other things like graphs or other stuff if you want as well. But anyways, this is the part that you want to focus on, is the stream bank part. We'll get to gullies in a second, but there's similar steps and a similar process we'll follow. So this is the part you've done. Now we're going to go back to the PLET screen and add practices. So I'm going to go back down here. I'm going to stop sharing. And I'm going to go back to the PLET screen. Can you see the PLET screen now?
Yes, I can.
Okay, great. Thanks, Isabel. Your technical assistance is wonderful. Okay, so same numbers as before I was showing you in Excel. The next step is to go back to our gully and stream banks tab. And here we're back to where we were before with the same areas that we inputted. But what we're going to change now is this BMP efficiency column. And by assigning an efficiency right now, there is no BMPs, so it's set at 0. What you want to do is make this number larger than 0, and it can't be larger than 1. So 1 being 100%, 0 being 0%. You want to assign what type of efficiency of stabilizing the slight, the moderate, and severe stream banks can be. So this can be complicated, but I'm going to pick some numbers here. This could be site specific depending on what practices you pick. But I'm going to pick 90%. And you do that by clicking here and where it's highlighted. And I'm going to pick the same 90% for the moderate. I'm going to pick 80% on the severe areas. Notice once you change these numbers that this little triangle comes up, which indicates that somebody came in here and changed the numbers. This platform PLET helps you determine quickly where numbers have been changed. Once you assign an efficiency, then a load reduction here in the lower right corner is shown from where you were to how much reduction or load reduction was achieved. So with these practices, we're assuming 90%, not 100% efficiency was stabilizing these slight, moderate, and severe eroding areas of the stream bank. So I'm going to click close here, which will take us back to the other screen. Just a minute, because I'm on a Wi-Fi signal here, so just a moment. And I'm going to go to the total loads tab again. And you can see what was, I think, 7 or 8. Now these numbers are smaller. And I'm going to go up here again to the download button to download this in Excel. And I'm going to highlight the same row like I did before to compare to the current. This is like the future condition here, or the stabilized condition post project. And I'm going to have to stop sharing and resharing because I'm bringing up the Excel spreadsheet now. Just a moment. So by clicking on the download button, this Excel spreadsheet comes up. This is what it looks like. Can everybody, Isabel, can everybody see this?
Yep.
Okay. Again, click total land uses again. This is the same information before that I was showing you. I'm just going to pull these out a little bit. I'm just going to select this row, which I'm going to copy. And I'm going to then go back to my other Excel spreadsheet, which is right here. And I'm going to paste that in. I'll make it really pretty with the color coding. And then from here, you can just do the quick Excel function. And then paste that in there. And then this is basically your quick report output. You could say we achieved of these categories here, or you can copy and paste this down here if you want to make it better that way. So in terms of sediment loading, we got 9.5 tons of sediment per year was stabilized after the practices, and 6.75 pounds of phosphorus. So that is the process for stream banks, and it involves being pretty careful about your field work and noting where those areas are and which sections are eroding or not eroding, and putting those inputs in here to get these outputs. So that is the stream banks. Now I'll go to the gullies, which will be a similar process, and I'll go a little faster because it's kind of the same steps. I see there's some questions here. I will try to get to those. Well, let's pause here for a second, and I'll try to answer some of these questions, and then we'll go to the gullies. How about that? Mitch, you asked, can the P load estimates in the model be used in lieu of physically sampling the stream bank or fields, thinking of water quality trading projects? Yeah, With water quality trading, the guidance I showed earlier, Mitch, in your question, it does require actually doing more measurements and taking actual samples of the soil types of the eroding areas in the pictures that I alluded to earlier. The guidance gets into that. For trading purposes, we want to be as site specific as possible, because that's the threshold we're trying to achieve with water quality trading, is a site specific analysis. This training I'm going through today is just more of a general, if you did a general grant for a conservation project and you want to do some load reduction estimates, for example, your land water plan, or for a trim grant or something like that, this method that I'm explaining today can be used. Hallie, you asked, is there guidance on efficiency? How do we know what % efficiency it is? Yeah, there is no guidance out there per se. It's more of a evaluation of how well you think those BMPs are going to stop the erosion from occurring. With stream banks, depending on the project the BMPs you're using, and also what type of storms or other types of flow regimes may be occurring that's interacting with that stabilized area, you may have more or less efficiency. In general, I can say this, that by let's say you pull banks back and then stabilize them with vegetation or native vegetation root wads and other structures, you're probably going to get a very high efficiency of stabilization versus just simply putting in some rock on one side of the bank and not rescaling back the slopes and things like that. You can certainly consult with DNR staff like myself, or water quality biologists, or non-point source staff into trying to define efficiency values.
We've also got another question come in directly to me, and that is on the recent list. So what is the septic related to?
What is the septic related to? On the recent list, is that the PLET page I was showing? Is that what? I'm not sure what the question means.
On the PLET page.
Oh, okay. Well, let me go there then. So the question relates to the inputs here or the loads? I assume it's the loads. And this is what the question referred to?
Potentially. I'm waiting to see if they clarify that.
Someone can just do a thumbs up, or
yeah,
okay, great.
It is.
All right, so this is what PLET does is based on some other inputs, which I can quickly show you here. It's going to estimate loading from different sources of land use or pollutant sources in the watershed. These septic numbers are not relevant to gully or stream bank projects today, but very quickly in the inputs, when you select this watershed, PLET will assign some values of based on 2012 inventory, the extent of cropland, urban land, and so forth. It'll also get into how many animals are in the watershed and the number of septic systems, which is shown here. Based on the number and the failure rate that are assigned to this, that's how it's assigning that number. In the training video that I said for using PLET, they make a very important point. These numbers are starting points. All these inputs, these red numbers shown here, they are not final. They should be, if you have more accurate information or can verify some of these numbers, they should be revised. And it's very applicable with septic systems. It's certainly applicable with animals, number of animals in a watershed, and how often manure is applied, and so on and so forth. So if you can revise these with more accurate information, you can change them by just selecting them like I'm showing here for forest, and you can revise them. Let me do it with the septics here. Let's say we know in this area there's 200 septics. You can click there and there's that. It will then change the loading rate for that. So it's a little tangent. That's the septic part to answer that question. Any other questions, Isabel, or can I proceed with the gullies now?
I think we've got everything that's been in the chat, so go right ahead.
Cool. All right. So for gullies, let's say, in addition to the stream bank project I already did, that you also stabilize some gullies that may lead to the same area of stream that you inventoried for the stream banks, or you find a gully that leads to that. Or it's a separate area altogether, for example, on a agricultural field, or maybe it's a forest land area where overland flow concentrates and forms a gully that leads to a stream. PLET can be used to estimate, if you stabilize that gully with vegetation or other practices, what the reduction is. And the way to do that is the same thing as with the stream banks. I'm going to go through the same steps now. Step 1, choose your gully. Step 2, assign the dimensions and the recession rates and what type of BMP efficiency is being occurred here. So I'll pick the same watershed. I'm going to pick gully 1. Let's say you measure this gully that leads to the stream and it's 150 feet long. And then you're going to put in the dimensions of the gully. And we're going to talk about what the dimensions of that gully is. The top width, I'm going to estimate that this example, the width of this gully is only about 0.5 feet, half a foot wide at the top. And at the bottom, it's about 2.2 feet wide, so a quarter foot. In terms of the depth, it's pretty shallow. It's only about half a foot deep. Next one, you have to pick how many years it takes for this to form. Does it form every year, or has it formed and then you are it's an ongoing type of gully? In this example, I'm going to assume that this is an annual erosion gully that is planted through or tilled through and replanted, and then it forms every year, year after year. And that may occur on agricultural settings. It may not be the same case with the forested segments, and you may want to pick a different number where it forms. I'm going to put 0 in here like we did before. We're going to assume it's the same clay soils like we did before. And I'm going to hit submit. So here's our stream bank information. Now we've added this gully information with these inputs, a 0% efficiency, clay soils, and there's your annual loading rate. And this is, I believe, of sediment here. There's also phosphorus also. I'm going to stop sharing this and show you another picture right now about gullies that I want to go through, and then we'll come back and do one more of these and then do the load reduction step. So this is not a very pretty drawing, but it's an example of gully erosion that I wanted to go through here today with you. Isabel, can everybody see this?
Yes, we can.
Perfect, great. So on the left, item 1 is an example of this entire area. This is a gully outline, the boundary, the channel, side drawing. And if you pick annual erosion, you're measuring this down saying every year, this amount of material is eroding from the gully each year. And these are the bigger numbers, if you will. If you have an existing gully and it's already there in the field, in item number 2 here, there may be some additional erosion as it continues to recede and erode, but it's not the entire area. It's just a small area that continues down cutting. In forested gullies and things like that, it's going to be a much smaller dimensions you're putting into PLET, because this isn't happening every year. Only a much smaller area is receding and eroding. So when you're talking about gullies, you want to understand these concepts. Is it the entire gully area that's eroding every year, or just a portion of it? And then accordingly put the correct inputs into STEPL for the gully erosion. Now I'll go back to PLET. So here, these are bigger numbers. I'm going to enter another gully. Again, same watershed. Let's call this gully 2. And this is the one that corresponds with the number 2 example I just showed you. And this is another 100-foot long gully, but the width of it is going to be smaller than the prior gully, because it's just the very bottom part of the channel that's eroding in a limited area, not the full channel is eroding every year. So I'm just going to say it's 0.25 feet. I'm sorry, half a foot. And the bottom is these dimensions. I'm just putting in some numbers as examples. And this is forming annually, but it's a much smaller amount. And hit submit. So we kind of got 2 examples, one that's forming every year and one that's just the example in line with the image I showed you earlier, just the smaller amount that's eroding annually. You can see there's a larger load and a smaller load based on the dimensions that you put in. So last step is to say, okay, we've identified what these gullies types are, their dimensions and so forth. There's no BMPs yet. We're going to go look at what the loading is by going back to this screen, hitting close. Sorry, I don't have any music to get us through the pausing here. And click on the total loads tab, which I just did here. Scroll down and here's the gully erosion rates. And from here, you can go and get the same information by clicking download in Excel. And I won't go through the same steps, but let me do this here. Let's just concentrate on the sediment load numbers. 1 ton and about 0.75 pounds of phosphorus is occurring from those 2 gullies that I've entered here. The next step is to go back to gullies and stream banks, identify your gullies and assign the BMP efficiencies. So here we can talk a little bit more about what's the right number to use. In some watershed-based plans, there are gullies that directly connect to streams or water bodies and are directly adjacent to a stream or a water body. So if you're stabilizing the gully with vegetation or other practices, your efficiency is going to be higher because of those reasons. It's right next to the stream and it directly connects to the stream. So I'll put 0.95 for this one. Now this other one that we entered here, this one doesn't directly connect to the stream, or it's further away, and there is no, but the topography says eventually water from this eroded area could still reach surface waters, but it's got to go through a vegetated area, for example, or a forested area. That's not that hasn't resulted in channelized flow. In that case, the efficiency may be lower than 95%. And in general, the further you get away, there's more opportunities for any soil or phosphorus from that gully to fall out and precipitate out, and less of it is going to make it to the stream. So I'm going to use a 0.75 number to account for less efficiency, because it may not directly, because of the topography or the physical connection, not all what's being eroded may be delivered to surface waters. Again, this is a site-specific determination based on some of the factors I just summarized. You can hit submit now. Oh, hang on. Oh, don't hit submit, because it'll ask you what additional things you want to add. Just hit close, excuse me. So now that we've added the efficiencies, that's what we're telling the model again is that we've stabilized these areas with an assumed efficiency of how well those BMPs work. And those loading numbers, which I'm waiting for this to come up under total loads, should be smaller. And they have shrunk down from 1 ton per acre down to 0.8. And where we were, this number is smaller as well. So again, I won't go through the steps again, because you've kind of seen that already with the stream banks. There's the before and the after, or with no practices, and then after practices are installed with those assumed efficiencies. And the difference between the two numbers is your reduction. So that's the kind of the step-by-step approach of how to use PLET for gullies and stream banks. And I see there's a couple questions here I can go through. That kind of summarizes what I wanted to go through with you all today. Stacy from DACCAP asked, are the correct inputs for gully only changing the geometry of the channel or adjusting the years to form? It could be one or both. And knowing years to form, that's getting at, is it happening every year, or is it only happening every other year or every 3 years based on more really bigger intense storms that may not happen every year? As far as the geometry, yes, that the geometry is the another way to accurately measure what's eroding or what part of the channel is eroding, and the corresponding loading from that eroding area or load reduction. Hallie from Trempealeau asks, okay. I'll get to Hallie's, and then Stacy asked another question here. Yeah, so Hallie, your question, is this related to sediment or nutrients getting to the surface water? What's PLET is predicting is, based on your inputs, is how much sediment or nutrients, in this case phosphorus, and there is a nitrogen component as well, is being transmitted or delivered to surface water. Stacy, your follow-up question or comment, some of our gullies are far larger and intense and carve out soils. Is PLET still applicable for such instance? It can be, yes. By actually taking on the ground measurements of some of these gullies, and you can categorize this through some catastrophic events like did happen in 2016 and 2018 in the Marengo and other watersheds, you can use this tool to quantify what those catastrophic events meant in terms of loading. And if that area is stabilized or through a restoration project, what type of load reduction was achieved. Okay, your last question, Stacy, is if the erosion's going on for years and years, how to enter years to form? My recommendation there is if you think it's been, or you can confirm it's been going on for years and years, through the field surveys or aerial photography or aerial imagery like Google Earth or some of our viewers and things like that, it's there year after year. That's what you've just confirmed it's annually. And you'd pick 1 year to form because it's happening. However, when you're measuring the dimensions of the gully, you're only going to try to measure how much that bottom of the channel is receding, not the total area, because it's happening year after year. And you're only accounting for the annual amount that's eroding at the bottom. A couple other questions here. Hallie asks, is there a section for groundwater? PLET does have a section for groundwater, but it's not that accurate. So and that's beyond the scope of today's presentation, but I'm happy to talk with you about that, Hallie, separately if you'd like. Katie asked, I can see BMP efficiency numbers being a challenge and varying quite a bit depending on who's entering the data. Correct. That's if some guidance could be developed with ranges and factors to consider for the higher loans, that would be really helpful. Yes, I agree. To do that, though, we would have to look at different parts of the state and different watersheds and assess erosion rates and things like that. And where the frustrating things becomes is we get into guidance, we get into the dilemma of saying, do we have enough sites that accounts for the variability in that watershed or that county or that area or not? And I agree, it'd be helpful if we had like some standard tables or numbers to go off of. PLET does provide some ballpark ranges for gullies, and as far as reporting goes for general grants and trim grant projects, at DNR, we're accepting this tool and its assumptions related to that. If you really want to make the modeling tool better, though, it requires a more site-specific analysis and echoing some of the principles of water quality trading, or a specific project, you can consult with DNR staff to better try to define what those site-specific efficiencies could be. Mitch, you had a comment. Great modeling tool. Are we going to start standardizing these tools so there's consistency for grant applications, land water plans? Yes, ultimately, standardization of tools is good. This webinar is an example of trying to get the word out about what this tool is and how it can be used to develop some standardization methods to be used. As far as the type of project, however, there may be, for example, like we talked about earlier, Mitch, with water quality trading, there's a higher level of analysis that may be required by statute or DNR policy. For trading, it's a little bit of both. And that would be a higher level or standard as shown in our appendix. But for grant applications, land water plans, I think what we have here is a good starting point or a foundation to work off of. And it can be made better with site-specific measurements like I've talked about here.
Yeah, Andrew, can you hear me?
Yeah.
So kind of what I mean is each county, does a very good job of doing their own thing and using, there's lots of models out there. It would be nice if everybody's comparing apples to apples with each, that's kind of what I'm asking is maybe some point I don't know how to get there, but maybe some point we will get there and say, if you're doing stream bank or gully practices, use this model. So it's kind of what I'm asking.
Yeah, well, good question. So this is one of the main reasons this is happening on a nationwide scale too, and this is why EPA came up with STEPL and now PLET, because different states had different ways of measuring things, and they didn't know if a pound of phosphorus from Nebraska was the same pound of phosphorus reduction from our state or Indiana per se. So coming up with some standard tool with standardized efficiency or load reduction outputs is one way to get there. The trade-off of that is that those assumptions behind those reductions may not be accurately reflected of what the state specific conditions are. So it's a quagmire, Mitch, of general versus specific, and there is no one right number or right method to approach this. I guess the last thing I'll say with modeling, and I saved this for the last, models are only as good as the inputs that are put into them and how well they are verified or calibrated. And STEPL or PLET doesn't talk about calibrating the modeling outputs or anything like that. That's certainly possible to do on a state basis or a county basis, particularly if some additional site-specific measurements are taken. For example, on a stream bank project, and there's the ability to either put in pins, erosion pins on the banks to measure a recession rate over time. And you can then compare what you observe in terms of the recession of the stream bank to what you put into STEPL or PLET when you did the load reduction estimates based on the visual cues that you used initially. That's one way to do it. Another way would be to go out and go additional verification steps of taking samples and all that stuff under the water quality trading approach. That's things we got a lot of time and a lot of resources to do that, and oftentimes it's not the case for us or for counties as well. Recognized models they're all wrong. They're never 100% right, but they are handy and valuable to represent what's going on in the landscape, and versus measuring everything individually, which could take forever, and we get into analysis paralysis. Well, we're at 11 o'clock. I expected this to take about an hour and 15 minutes, so I don't have much other content unless there's additional questions specifically about gullies or the stream banks. Isabel, we talked about there may be interest in seeing other aspects of PLET being demonstrated. Again, the training video that's already on the PLET webpage goes through all the functions of using PLET, not only just the stream banks and gullies that we went through today, but the cropland and specific cropland practices and how that makes reductions. Same thing for septics and other BMPs as well, including urban BMPs. So I encourage you guys to look at that. And if you'd like or are interested in another session like this that I could do, I'm willing to tackle this step by step with you guys if there's interest. Isabel and I talked about this, saying that we'll let you guys be the demand of the audience. How much or how little information do you want or need? Stacy asked another question here I just saw. Is there a lot of difference between entering 1 year versus half a year versus 1 day and years to form outputs? Is 1 day way worse than 1 year or vice versa? Let me try to answer that right now. The metric here, I'm assuming you're talking about the gullies. Isabel, again, can you guys see this screen?
I cannot see any screen shared.
Okay, I clicked too fast again. Sorry about that. I'm getting it, guys. Thanks for your patience. We're getting there. There. Now you should be able to see it.
Yep, we can.
Yeah. So it's only about years to form. What if we change this number to like half a year or things like that? Can do 0.5. Or you could do 0.05, for example. And by doing this, Stacy, you can then see what the corresponding loading rates are. here at 0.05, so this is much more frequently. The load is increasing, and if I go back to 1 year, it's going down. So I think I answered your question. The more frequently this happens, you know, every 6 months or every the smaller the number, the bigger the load, and vice versa. The more years it takes to form, the smaller the load. I just changed it to 2, and now it's half that number. Awesome. You're welcome, Stacy. Yeah, so this, I'm happy to answer any other questions if there is. If not, you're welcome to contact me by email if something comes up. If you review this at a later time or other staff do it and you guys still don't understand something, please give me a call or email me, and we can set up a time on Teams and we can go through individually what PLET file you have. Like I said before, in PLET, I'm sharing the screen again. Yeah, it worked this time. Great. You have the ability, if you create a PLET file, to share it with others by clicking this share model button. And I think what happens here, let's think through. It'll ask you to enter an email address, and then this tool can be used as a sharing platform as well. Yeah, there you go. And you can make copies of it as well, so you don't manipulate your original and so forth. Fantastic. Well, thanks guys for your patience today and your questions.
And thank you so much, Andrew, for presenting today. Just for everyone else, I'll be sending out that evaluation link. And like Andrew said, we'd love to hear your input on if you want more specific things or anything like that. So please make sure to fill out that evaluation. And then there'll be that link to the recording. So thank you, everybody. And thank you, Andrew.
One more thing. Tomorrow, there's another session we have planned that I'll be back again talking about apple lots. So come back, tune in again.
Absolutely. Yes. Everybody, please do that.